Welcome everyone. So this is our 36th live stream geometry. And today I am going to take problems from the Serbia Math Olympiad. So I'd never seen these problems before. Somehow I missed it, but they look really elegant. Most of them have a simple statement, but they don't look that easy to solve. So we have 3 people here with us right now. And so from Azerbaijan, Vietnam, and Turkey. So we got a good mix of people all over the world. And so with that, let's jump right into it. So I'm going to share my screen. All right. Can you all see GeoGebra? All right. So here's the first problem. So we have a triangle ABC with orthocenter O. I'm sorry, circumcenter O. All right. Probably gonna have to make some more room later. And let me draw on the circumcenter. So O is the center of that circle, which is circle C in GeoGebra. And then we draw the circumcircle of BOC. So, and we have some line is tangent to the circumcircle of BOC. So I could just draw like a random point and then the tangent line at that point. Yeah, it's making me admit each person into the meeting myself, so they don't automatically join. I'm not sure why. It used to just let everyone in, like the moment they join. So it intersects it at D and E. So let me rename this. I don't know. We could just call it like X, let's say. And D and E are the intersections with AB and AC. And then we reflect A over DE. And that's A prime. And then we draw the circumcircle of A prime DE. So let me adjust the diagram a little bit. So yeah, something like that. Okay. So if I draw the circumcircle of A prime DE, it's saying that that's actually tangent to the circumcircle of ABC. That's what we have to prove. So yeah, I like these problems from Serbia. They're like pretty simple statements, but I don't think this will be that, I don't know if it'll be that easy to prove. I don't think A prime DE is isosceles. No, there's no way. So I see psi just joined. Oops. I think something might have went wrong. Somebody tried to join, but I hope I didn't decline it for them. Okay. So yeah, if we move X around, yeah, the point of tangency doesn't stay the same because I can like, yeah, but we want to show that they're tangent. Maybe I could show like most of the circle. So obviously BO equals OC. So O is the midpoint of arc BC. Where can we go from there? Oh, psi was able to join. Hey, psi. Yeah, I'm not even sure really where to begin with this. This looks like a really hard problem. Maybe I could let, you know what? So we don't actually know their tangent, but maybe I could draw the maybe DE, BC and the tangent at F concur. Or maybe the tangent at F is the reflection of DE over BC. Let's see. Yeah, okay. So DE intersect BC. Actually, maybe this isn't as hard as I thought. I wonder if, let me draw the tangent at F. I don't think it passes through that point. No. Okay, so I'm going to label this intersection point as G. All right. And maybe we could use power of a point a couple times. So gx squared is gb times gc I wonder if BDEC is cyclic. I don't think so. Right? No, I think it's very unlikely. I'll just check it though. Yeah.
Hi.
Hello. How are you? Thanks for joining.
Hello. I think BDFX is cyclic.
BDFX
and
is cyclic.
X is CF.
BDCF.
Because in such problems.
Interesting.
No, BD. It is Michel point. I think in such problem, the tangency point.
Okay,
is actually somehow the Michel point.
Okay, so showing BDXF is cyclic, that seems like it has to be an angle chase, right? So angle DXF, it's angle, we want to show that's, maybe I should label this point and this point. So you said something about Michel points, right? Hold on, I'll check the chat in just a second. Just want to label these points. Okay. But how did we define F? Yeah, I kind of already assumed they were tangent when we don't know that. So yeah, I can't really, I'm kind of cheating there. Yeah, I'll delete F for now. So, okay, so what we should do, maybe we should let the circumcircle of BDX intersect. So yeah, we could show that these two circles concur on the circumcircle, and then we could show that that common point is the point of tangency and is cyclic. Yeah, well, maybe we could approach it that way instead. So, okay. So first, is it obvious that these two circles meet on this circle? Maybe that's just an angle chase, because it basically, okay, we could first draw one of the circles, right? And we could let it intersect at F. And then we could try to show that FXEC is cyclic. And I think that's probably just an angle chase. So then we could show that the other circle, so yeah, I'd have to actually do the angle chase, but I wouldn't think it would be that hard. Okay, so yeah, so then we could draw the other circle, and then we want to show that A prime FDE is cyclic, and that might also be an angle chase actually, because we want to show angle, because angle DA prime E is the same as angle DAE, and we want to show that would be equal to angle DFE, but we could break up DFE into DBX, so that's also an angle chase. So then we could show that DF A prime E is cyclic. And now we need to show those circles are tangent. And maybe that's also an angle chase. Is that right? So, actually, I'm not sure if that is that easy. How we would have to show those two circles are tangent, right? I wonder if F changes if you change X. I was going to try to use homotheties somehow. Does Fx meet at the midpoint of arc BAC? Let's see. If I draw, no, that's not the midpoint of arc BAC. So yeah, how do we show those are tangent? Yeah, we might not need point G, but I'll see. So to show that they're tangent, yeah, we could try drawing the tangent to ABC at F. I kind of like that. And maybe we could let it meet BC at a point, and then we could show that that's also tangent to this other circle. Not sure how we would do that though. Yeah, I'll draw both these points maybe. So we draw the tangent to one of the circles and we want to show it's also tangent to the other circle. Can it be done? Maybe it can be done by an angle chase. So we would want to show angle BF. Yeah, maybe. So yeah, if we could show angle, I think if we can show angle BEF equals angle B, no, that doesn't seem right. Because DFJ, so DFJ, yeah, so maybe we need to let FD meet the circle, meet the bigger circle at a point. So maybe something like this. So then we would want to show that DFJ. So we'd have angle DFJ is DEF, and then yeah, I'm just not sure. So yeah, I agree with DEF. We can show DFJ is DEF, and we can calculate that.
Michael. If we let FD cut the circumcircle as well as let FA cut the circumcircle at a point, another point. So from Pascal, we will have that maybe we're gonna prove that LX C is collinear and MX B is collinear. Maybe, just maybe.
Oh, so okay. Let's see. So Hakan thinks he has the answer. So the Pascal looks interesting, but yeah. First, I'm going to read. So angle BFJ. Okay, so you define the tangent to be, okay, so the tangent is defined to be to the circumcircle of ABC, and then you're showing it's also tangent to, okay, so you're showing BFJ is DFB plus BFJ, DFB is DXB, and BFJ is BCF, because, okay. And then, all right, I think that does it. So yeah, I don't think we need Pascal, although it's an interesting idea.
Okay.
But yeah, it does sound interesting. So yeah, maybe I'll check it out after after the session today. So I'm going to delete point, I'm going to delete G, and let me just draw J, just J. So yeah, J could really be any point on that line. In fact, I don't even need to draw the extension of BC, I think. I could just let J be some point. I'm going to change it to J just to match what Hakan just wrote. All right. Okay, so let me type it up. Just a second, let me move some stuff out of the way. And so we have let the circle dbx meet ABC at F. And then we want to show F is the common point of tangency. So first we're going to show CEXF is cyclic. Did we even need that? That CEXF was cyclic? I'm not even sure if we needed that. Let's look at the angle chase. So you have XCB here. Okay, so we do need it. Okay. All right. So first I'm going to show CEXF is cyclic. So we have angle CFX is angle BFC minus angle BFX, and that is BFX is ADE. Okay, thanks for typing it up. That's a nice angle chase right there. So you have angle FXE is angle ABF is 180 minus angle ACF, 180 minus angle ECF. And so that means that, let me just check it one more time. FXC is ABF is 180 minus ACF, it's 180 minus ECF. So FXCC is cyclic. Is that just Meckel's theorem somehow? I don't even know. But yeah, maybe it is just like a Meckel point. I think that's what, I forgot if your name is Dan, but okay. So this means that CEXF is cyclic. And once we know that, now we can do an angle chase to show that A prime E df is cyclic. So, oh, that is the Meckel's theorem that you mentioned. Yeah, okay. So yeah, if you have any segment like this and a point on it, then those circles will concur. Oh, actually, that's just the Meckel point of triangle ADE with respect to X, B, and C. Okay. So I'll just say alternatively use Meckel's theorem. All right. And then we have angle DFE is DFX plus EXF. Did you already write this? Not yet. So yeah, I'm going to write it out. So angle DFE is angle DXF plus angle CX. And that's angle DBX plus angle ECX. Okay. And where do we go from there? We need to show that that's equal to angle A. Is that obvious? So let's see, DBX is ADX. DBX is XCB. Why? Wait. Why is DBX XC? Oh, I think you mean XC. Don't I mean EFX? EFX plus E. Yeah, EFX, you're right. Good catch. So that should be EFX. But DBX is XCB. I don't see why that's true. I think it's XCI, not XCB, right? It would be XCI. So I mean, so it's I think it's ADX minus BXD. Yeah, okay. So that's ADX minus BXD. Let's see. There we go. Let me put let's see if this works. Cross your fingers, hopefully it'll work. Yes. And then plus ACX minus CXE. And ABX, so oops. Sorry. BXD is, so BXD is the same as XCB. I don't know if I'm going in a circle here. Yeah, okay, I think I'm getting here. And then ABX, Isn't dbx the same as abx? Yes. So, yeah. So this is wait, no, isn't dbx the same as abx? Oh yeah, I think this should be a dx. I'm sorry. There should be a dx, and this should be a ex. Good point. And okay, there we go. And a dx is the same as bfx. All right. So this is bfx. bxd is 180 minus 2a. Okay. So I like it. So I'm just going to rewrite this. So this is adx plus aex. Oops. And then minus exd plus cxe. And then now we can do what Hakan wrote. So this is just 180 minus a minus 180 minus twice angle A, and that's just equal to angle A. And that is equal to angle dA prime E. See how this looks. Let's check it. So DFE, it's dfx plus EFX, which is dBx plus ECX, and dBx is ADX minus BXD. This is AEX minus CXE. We then rewrite it, and ADX plus AEX is 180 minus A, and BXD plus CXE, that's 180 minus twice A, because it's 180 minus BXC. So I'll just break this up into two statements. Just for clarity. And then there we have it. So there is no 2 before angle BXC. Oh yeah, you're right. BXC. Good point. All right. So DEA prime F is cyclic. And then once we know that, let J be an arbitrary point on the tangent. I'll say draw the tangent to the circle ABC at F. Let J be an arbitrary point on it. I'll just say on the side shown. Whoops. We don't need the double backslash. And then now I'll do the angle chase that you wrote. And then that will finish it. Just a second. Have I never closed this yet? Wow. Okay, so let's do this. And then I will move on to the next one. Yeah, well, when I do copy paste on the word angle, it messes up the spacing. So I prefer to just type it out every time, but yeah, maybe there's a better way. Let's see. Break it up into 2 lines. See how this works. There we go. So dfj is dfb plus bfj. dfb is dxb plus bcf. And then dxb is xcb plus bcf, which is xcf, which is xef, which is def. Beautiful. So that means that jf is also tangent to the other circle. So jf is also tangent to a prime be, and that means that a prime be is tangent to abc. Awesome. This is a fun one. So thanks everyone for your help, and now I will move on to the next one. All right. So short statement here, but we'll see if it's really that easy. So we have an inscribed. So let's think. So for just for drawing problems like these, I often think it's easiest to do it like this. So I actually looked at this problem a little beforehand. So I think the easiest way to draw the diagram would be like this. So I'm going to draw the in circle of PBC. Let me use the algebra tool. So we have a circumscribed quadrilateral. So here's the in circle of PBC, and I'll let I be the center of it. And I'll pick a random point here. I'll rename it something else. Let's call it E. And I'll draw the tangent at E. Let's see. Where's the tangent? There we go. Hide that for now. I don't know if I'm going to want to show it again later or not, but for now I'm going to hide it. And the circumcircles of PAB. Oh, did I do this right? Oh, AD and BC. I'm going to have to rename the points. Oops. So this is A, B, and then C, D. And we draw the intersection of the circumcircles of PAB and PCD. And they meet at X. Okay. So maybe I'll move the diagram a little bit. And then we draw the tangents from F to the circle, from X to the circle. So basically, I don't think I'm going to need this algebra anymore. Let's draw tangents. So it says, prove that those two tangents make equal angles with AX and CX. So what is that? How would I write that out? So AX. Okay, we want to show those two angles are equal. So let's say I draw the tangents. Let's draw the points where they meet the circle itself. Let's see if I can do it where it's easier to see those tangency points. What if I draw like a really tall triangle, kind of like that? There we go. So this kind of reminds me of my video I did on my 1,000 subscriber video, where it's kind of hard to see the tangency points. But if you draw it like that, then, okay, so we want to draw XF and XG. Should we draw where they meet the circle, the big circle? I don't know if that would be that helpful, but maybe. Why not? All right. So we want to show angle GXA is equal to angle FXC. Now E doesn't lie on this, so I don't want to make it look like it does. There we go. Second, guys. Sorry. It's enough to prove XI is the angle bisector of AXC. Do we know that XI is the angle bisector of HX? Oh yeah, no, you're right, yeah, because obviously XI bisects GXF. So yeah, I see what you're saying. Hold on just a second, guys. I'll be right back. All right, thanks for waiting. All right, so we need to show that XI bisects AXC. That is interesting. So yeah, I'm not even sure how to start with this. Yeah, it looks doable. Yeah, we don't need the tangency points. Okay. Yeah, I'm not going to erase them, but yeah, we don't need the tangency points. That's a good observation. Is it worth letting AX meet the circle at a point? I don't know. Maybe we could use the isogonal line lemma. So yeah, that makes it look like it should be an easy problem. If we can use that X as the McKell point. So I mean, XAB is similar to XDC, right? By a spiral similarity, I guess. So if XAB, triangle XAB is similar to triangle XDC, maybe that makes it DXB. Yeah, I think by symmetry, that would have to be, yeah, because a spiral similarity takes triangle XAB to triangle XBC. And so, yeah, if one is true, the other is also true. Yeah, it seems like it should be easy. Let's see. So can we show angle AXI is angle CXI? Maybe polars. I wonder, what if we use the isogonal line lemma? So we have XD, XA, XB, and XC, and I think we know that those are isogonal. So DABC I think if we let BD intersect AC at a point, then this point and P are isogonal. I wonder if X at this point and I are collinear. No, they're not. So I is the X center. What do we know about X centers that we could use? Maybe we could show I is also the X center of so yeah, what's the X center of triangle XAC? So I wonder, let me try something. If we extend XA, is I on the angle bisector of this? I doubt it's on the angle bisector of that. Yeah, I'm not sure what I'm doing actually. Wait, I wanted to find the X center of XAC. So that would be where those meet. Yeah, I don't think that does much. Could we use the in-center X-center lemma? So what if I draw the in-center of triangle PAB? I would need to do this. Let me try to use the in-center X-center lemma. So and what's the center of that? What's R? So I'll say K is the center of R. And then AKBI is cyclic. So PK and I are collinear, right? And I don't know if it'll help to draw this point. AKBI is cyclic. See what that does. But yeah, this circle AKBI isn't necessarily tangent, but the other two circles are. Yeah, maybe I could just for now hide, do what Hakan suggests, just hide the points of tangency. And I could add them back in when I do the proof. So this is the midpoint of arc AB right here. And this is the midpoint of arc BC. So XAMB is similar to XDLC. So this is interesting. Basically, we want to show that the angle bisectors of APC and AXC both pass through I. That looks very familiar, showing that two angle bisectors pass through the same point. So XAMB is similar to XDLC. So what would I is like, is there like another triangle that both of those are similar to? XAB, XDC. All right, we have someone else joining. Yeah, it seems like it should be doable. What do we know about two angle bisectors meeting at the same point? Is there something like with Apollonius circles that would come into play here? Oh, I think that would mean that PX, oh, because PXAC, wait a sec. If you look at, so if you draw CI and you let it meet XA at a point, by the way, does CI pass through this point? I don't think so, but that would be interesting. No, there's no way it could. But basically, if XA intersects CI at a point, actually, no, actually what I want to do, I don't think I did this right. I want to draw AI and let it meet PC at a point. And then I want to show that that point is cyclic with x, px, and a. So if I let these two meet at a point, and that point is cyclic with ax and p, then I think that solves the problem. Let me unhide point E. Yeah, I'm just trying to make this look nicer. I want to be able to see this intersection. It's hard to draw it, but I move E, there we go. So moving E helps. And what did I want to do? I want to show that PXAN is cyclic. Let me check if that's actually true, because I don't think it is. No. What did I want to show? So I want to show that the angle bisector of X, AXC and APC. Oh, you know what? Yeah, I don't think that this is going to work. Yeah, let me just undo a bunch of steps here. No, I want to show the bisectors of, yeah, AXC and APC. I want to show they pass through I. Yeah, I'm not sure. Let me go back a little bit, because yeah, this diagram doesn't look the greatest. So the orthogonal line lemma work. P. So if we draw the intersection of AB and CB, I think those two are actually isogonal with XA and XC. So I think what we could do is let AB intersect CB. And if we do that, I want to be able to see the intersection. Then I wonder if angle NX, I wonder if XI bisects angle NXP. So let me check that. Whoops, sorry. It used to always give you the acute angle. I wish it still did that. So, or the angle less than 180. So is this a bisector? Yes, okay. So by the isogonal line lemma, I think we need to show that angle PXI is equal to angle NXI. And I wonder if that's just like angle chasing or something. maybe n is the reflection of p over xc. I'm not sure about that. I would be a little surprised if that were true. Angle chase. We can use yeah, so it's not the reflection, but we can use, you're saying we can use angle chasing to show that nxi is pxi? So write out a little more. That's right. So pxi, is there a way to break that up? Maybe Ricard's theorem. I'm just thinking. Let's see. Hold on a sec. Let me get my. Let's see. Okay. So. I see Bob join. All right. What was I thinking of doing here? Oh, nxi equals pxi. Can we show that? So yeah, px and n are not collinear. But okay, so I think we have by Michael's theorem. Yeah, I think we would need a. So is it? So NAXD is cyclic by Michael's theorem, right? Yeah. And then maybe it's in. And NXBC is also cyclic too. So can we show NX? So I think we could probably show easily that NXA is PXC because NXA, yeah, is PDC is PXC. So yeah, we have a lot of information here. Just have to find a way to finish it off. So wait, we want to show that, I is on the bisector of PXN, and we know it's on the bisectors of all three of these angles. Wow, this is tricky. It's almost like I want to show I is the X center of a different triangle. Yeah, this is such a weird problem. So I wonder, so we know that XDLC is similar to XAMB. Does K correspond to I in that similarity? I don't think so. But what does correspond to I? So M is the midpoint of IK. I forgot that. M is the center of this circle.
M is the center of what?
M is the center of this circle through A, K, B, and I.
Okay.
You guys want to move on to the next one or try this one for like 5 more minutes? Yeah, it's only 12:10 right now, so yeah, we still have a while. Let's see.
Is there any use of the fact that AB plus DC is equals to AD plus BC?
Maybe. Yeah, that's Pito's theorem, right? Yeah, maybe.
Right. Maybe we should look something else than angle chasing.
Okay. All right. Hakan thinks we can move on, so I'm going to move on. But I could, yeah, let's get back to this in the end. It's a good problem.
Yeah.
All right. I feel like this is like another isogonal problem. Let's see. We have a triangle ABC, and first I'm going to draw the circumcenter O. So O is the center of C. And now I'm going to draw what looks like the 9-point circle. So draw a bunch of midpoints and I'll rename it MN and P. So this is M. This is N. And this is P. And we draw the so the 9-point circle basically. So we want to see where MNP and BOC intersect. And basically we just want to show those are isogonal with A and C. So X and Y, it doesn't matter really which is X and Y for the problem because we want to show those are isogonal. So I guess I might as well draw the feet of the altitudes, right? So obviously D is the foot of the altitude, and same with E and F because of the 9-point circle. Can we use the isogonal line lemma? So we'd want to let BX and CY intersect, and we want to let BX and BC and XY intersect. That doesn't look super useful to me. Let's see, check the chat. Inversion. Okay, invert with center A and radius AF times AP. So what would that do? What would that do to the circle BOC? Yeah, I'm not sure. So we want to use that. This is the 9-point circle. What do we know? Maybe I should draw the circumcenter, right? Or I'm sorry, the orthocenter. So let me draw the orthocenter. And I'll call it H. What do we know? So a homothety takes the 9-point circle to the circumcircle. Since BO is equal to OC, we often get stuff about like angle bisectors and stuff like that. Isn't there something about like so what is the Dumpty point? I think there's like a connection. The Humpty point is the perpendicular from the orthocenter to the median. The Dumpty point, I think, is the, so you draw like the symmedian. So yeah, what if I try drawing? Yeah, the midpoint of the symmedian chord, yeah. So what if I tried drawing that? Let me add a little bit more. I just feel it's often helpful because like, So yeah, those are the two tangents to the circle, and I think they meet on the circumcircle BOC. So maybe I should shrink the figure a little bit, and maybe I should draw the symmedian. Let's see what I can use on dumpty points. So here's the symmedian, and I think this is the dumpty point right there, right? Yeah, so this is the dumpty point. And it's the isogonal conjugate of the Humpty point. What just happened here? I thought E and F. Oh, something is weird. Where did my 9-point circle? What happened to my 9-point circle? Okay, I guess I shouldn't be. F is the midpoint. What's going on here? So yeah, I don't know what happened to my 9-point circle. Didn't I have all 9 points? It's weird. Anyways, let me draw this point and this point. So C, H, and J, I think should be collinear, although they don't look like it. Maybe I drew the orthocenter wrong. Yeah, okay, I drew the orthocenter wrong. So, because it should have been this instead, okay. So this is the real orthocenter. There we go. So G and M are isogonal, right? And OM and G are collinear. So G and M are isogonal, and we want to show X and Y are isogonal. Could we use the isogonal line limit somehow? Sorry. So where do GM and XY intersect? Yeah, this is hard. So let me draw the 9-point center. So that's the midpoint of OH. I could call it N to show it's a 9-point center. Are I, N, and M collinear? I don't think that's true, but I could check it. No. So this is the 9-point center, and a homothency about H takes the 9-point circle to the circumcircle. So where does it take X to? So maybe I should draw HX and HY. So if we want to show BAX is CAY, if I shrunk, so if I do a homotopy about H, and I try to shrink BAX in half, yeah, basically I would want the midpoint of HX. Hold on a sec. So what is the center of this circle? It would be the midpoint of OG, right? So if I take the midpoint of OG, that Q is the center of that circle. Oh, it does? Okay. So let me try root BC over 2 inversion. Hold on just a second. Okay, so the 9-point circle would get mapped to the circumcircle BOC. And so basically X and Y would have to get mapped to each other is the idea, right? I think that's what you're saying, right? Very interesting.
Yes. The root inversion make the 9-point center to the OBC center circle. Yeah.
Okay.
So yeah, X and Y. Yeah.
So how do you prove that they map to each other? So I guess you could see, so O and D swap places. Okay. And B and K swap places.
Yeah, C and F.
And C and I think you mean C and J, right? Oh, sorry, B and E and C and F swap places. Interesting. Okay. So first, how do we show that? How do we show that B maps to O? That might just be a well-known fact. I'm trying to remember.
Yeah. Just let AO meet the circle at some point.
Okay.
So you will have that triangle ABD similar to triangle A prime C. Yeah.
Okay. So if you do a root BC over 2 inversion, triangle ABD maps to A prime C because it swaps, B and C get swapped, and okay, so I see how it swaps B and C, and then because it preserves angles, it has to map. Yeah, I'm still not 100% sure. So let me delete some stuff that I don't think I need, or I'm just going to hide it just because I don't know. Okay. So let's see. So is it a root BC inversion or a root BC over 2 inversion? Okay. So, okay. So it's because E is the midpoint. Do I have 2? Did I label 2 points here? Whoa. Hold on. I think I labeled this point twice. Oh, because I called this, yeah, let me call this n again. And I don't even know, what did I do here? Why does it say E and F? Let's see. I just want to hide this point F. There we go. Okay. We'll just call it R. So let me use the root BC over 2 inversion. I guess I'd rather try to like explain the concept on my channel if I can. So we want AO times AD is AB times AC, and is AB times AC over 2. Okay, so but I think it's very simple because we just have triangle ABD is similar to triangle AON, and I think that's all we need to show that. So, so basically we have angle BAD is angle OAN, which is well known. And so that implies triangle BAD is similar to triangle OAN. And so, what happened here? Oops. And so AB over AD is AO over AN. So that means that AD times AO is equal to AB times AN is equal to AB times AC over 2. So an inversion about AB with radius that will swap D and O. So that swaps D and O. Oh, I'll say followed by a reflection about the angle bisector of A. All right. So that's from the above information. And then it also swaps B and K, I'm sorry, B and E, and, or I'm sorry, B and N with the new notation and C and P. So it swaps B and N. This same swaps B and N. I think it's B and N. And also C and P. Let me just give a name to the inversion / reflection. We'll just call it phi. And so therefore phi takes the circumcircle of BOC to the circumcircle of DNP. So DNP. So yeah, I'll just add one more step here, just using the 9-point circle. Passes through the A altitude B. Okay, so, and then once we know that, therefore, angle BAX, since X and Y are on both circles, they have to be swapped by phi. And that means that angle BAX is equal to angle CAY, because it's a inversion followed by reflection. Very cool. Very nice solution using root BC inversion. All right, so I'll move on to the next one. It's just 1234, so we're just about halfway. So we have a trapezoid ABCD. See how I want to do this. AC and BD intersect at E. Okay, let me draw. I see where this is going, I think. So we want to draw the altitude